This video is on ice charts. So when a problem gives you initial concentrations and not equilibrium concentrations, you must make an ice chart. And this is a chart that allows us to solve for equilibrium concentrations when a stressor is applied. So we've learned about Le Chatelier's principle, and in Le Chatelier's principle, when a stress is applied to a system, it's going to shift either to or away from that stress in order to alleviate it, so that way it can get back to equilibrium. So we're going to use some math to do some calculations to figure out what those concentrations are given an initial shift in our equilibrium. So we call it an ice chart, where I stands for initial, C stands for change, and then E stands for equilibrium. Okay. There's a stoichiometric change in equilibrium reactions just like regular reactions. So we learned in our moles and stoichiometry unit that our reactions are going to change based on those coefficients in front of our balanced reaction. Those are our mole ratios. So we use mole ratios to determine the amount of products formed. And we did that where we set up our chart and we had moles of A to moles of B, and we have a number here and here. We're going to use that ratio, the coefficient in front, to help us determine the amount of our concentrations in equilibrium. So, for example, 4 moles of HI, so hydroiodic acid, are placed in an evacuated 5-liter flask and then heated to 800 degrees Kelvin. The system's allowed to reach equilibrium. So what will the equilibrium concentrations be? So we have our reaction here. This is already at equilibrium because of our double arrows. We're going to apply 4 moles into this 5-liter flask. So that tells us we need to have our concentration of our HI. So our concentration of HI that we apply, our stressor, is our 4 moles divided by our 5 liters, which is 0.8 molar. So that's what we're starting with. We want to know the equilibrium. So to do that, we're going to fill out this ice chart. So initial concentration, that's I, change, C, equilibrium, E. Okay, ice. We're going to let X represent the change in concentration of the hydrogen gas. So we start with HI alone. We determined we start with 0.8 molar HI. So initially we have 0.8 molar HI. We have no hydrogen gas, no iodine gas. If we add a stressor, we're going to shift away from what we add. So my change is going to be shifting towards my products. When I shift towards my products, I'm going to take away some amount of my part I've added. I'm going to add some amount of each one of my products. And the ratio of each of these is based off of their coefficients. Remember, that's our stoichiometric mole ratio. So my coefficient here is a 2, a 1, and a 1. So at equilibrium, this is going to happen, so I'm going to add it together. So 0.8 minus 2x, 0 plus x, 0 plus x. So at equilibrium, this is what I'm going to have. I know my K value is 0.16. So just like before, we can write our equilibrium expressions, set equal to KEQ. I can do the same thing here. This is my equilibrium concentration, and those are the numbers I'll use for my equilibrium expression. So I would set up KEQ, my first step. Then I would plug in my E line and solve for X. Once I've plugged in this line into my KEQ expression, I can then solve for my X, and once I have my X value, then I can plug my X value in to get my equilibrium concentration. So then I would plug X value into my E line to get my equilibrium concentrations. Okay, so let's go ahead and do that. Now this is the new part. This is the chemistry. After this, it's just math. Okay? So, here I have a similar equation. Hydrochloric acid decomposes into hydrogen gas and chlorine gas. Okay, notice I'm at equilibrium. I'm starting with 0.6 moles of HCl in a 2-liter flask. So I need to get its concentration. 0.6 over 2 gives me 0.3 molar. That's my initial amount. So I have my ice chart, ICE. Initially I'm starting with my 0.3 molar HCl. Once I've added this to my equilibrium, my system is allowed to establish its equilibrium again. So to do that, I have neither of my two products, so I'm going to shift towards my products. So I shift away from what I've added. That means that I'm subtracting away some amount, and I'm adding some amount to both my products to get to equilibrium. And remember, this change is based off of my mole ratio. So 2x, 1x, 1x. Then equilibrium is where I added them together. So 0.3 minus 2x, x, and x. Okay. So now I've set up my ice chart. Now I can start solving for x, so I can figure out what these numbers are supposed to be, because that's what I'm looking for. So I'll write my KEQ expression. So part 1, write my KEQ. KEQ is equal to products over reactants raised to their coefficients. Cl2 over HCl. Remember, it's 2HCl, so it's HCl squared. Okay. So that's my equilibrium expression. Now I'll plug in my E line, so this line here, into my equilibrium expression so I can solve for my x. So KEQ is equal to 0.5. So 0.5, this is step 2. 0.5 is equal to x times x, because H2 is x and Cl2 is x, over my HCl, which is 0.3 minus 2x, and that's squared. Okay. So that's what I'm starting with. That was the chemistry. Now it's just math. I have to solve for x. So to solve for x, I'm going to 0.5 is equal to x squared, x times x is x squared, over 0.3 minus 2x squared. If I have a squared on the top and a squared on the bottom, I can take the square root of both sides. So square root of the left, square root of the right, square root of 0.5 is 0.707 is equal to x over 0.3 minus 2x. Okay, I'm going to bring this up. 0.707 times 0.3 minus 2x is equal to x. Distribute through. 0.212 minus 1.414x is equal to x. I have x on both sides and it's subtraction, so I'm going to add 1.414x to both sides. Bring this up here. When I add it to both sides, this is 1x plus 1.414x. So 0.212 is equal to 1 plus 1, 2.414x. Divide both sides by 2.414. And I get 0.088 is equal to x. Okay. Now, step 3. I plug my x value that I found into my equilibrium line. So this gets plugged into here, so that way I can get my concentration. So 0.3 minus 2 times my x is going to be 0.28 molar. Then I have x, which is 0.088 molar, and x is 0.088 molar. So I've determined that at equilibrium, my HCl is equal to 0.28 molar. H2 is equal to 0.088 molar. And Cl2 is also equal to 0.088 molar.